Now see the magnetic properties of matter. Magnetic properties of matter. So as we have defined, there are three categories of matter. So on the basis of magnetic dipole moment of atom, magnetic dipole moment of atoms, the matter has been classified as the matters has been classified as. So first we can say diamagnetic material, and second is a paramagnetic material, and third one is ferromagnetic material. Ferromagnetic material. So first is the diamagnetic material. Diamagnetic material. See, in diamagnetic material are made from those type of atoms who do not have any magnetic dipole moment. So diamagnetic materials are made from the atom having no net magnetic moment. So when these materials are kept in external magnetic field, so a induced magnetic moment you develop inside the material, and that induced magnetic moment is trying to opposes the external magnetic field, that is according to Lenz law. So resultant field inside the material become here less than the applied field. So this is the main characteristic of diamagnetic material. So we can write here, so diamagnetic material these materials are made from atoms which do not have net magnetic moment, which do not have net magnetic moment. So when these materials are kept, when these materials are kept in external magnetic field, in external magnetic field, a magnetic moment will develop. A magnetic moment induced inside the material, a magnetic moment induced inside the material which opposes the external magnetic field, which opposes the external magnetic field, So resultant field So resultant field inside the material decreases. So examples of such materials are water, sodium chloride, nitrogen at STP, etc. So these materials, these are called the main point here. Now, so magnetic lines of forces. The magnetic lines of forces repelled by these materials, or we can say when these materials kept in magnetic field, so these material will shift. So material will shift from high magnetic field to low magnetic field region. So we can have this type of diagram. Suppose this is any diamagnetic substance and this is the lines of forces. So when the lines of forces are coming here, that lines of forces may go like that. That can be said these lines of forces are just avoiding the material, or they are going away from the material like this. This is the lines of forces here. You can see in the diamagnetic material. Now, the perfect diamagnetic material is type 1 superconductor. The perfect diamagnetic material is type 1 superconductor. It has magnetic susceptibility or -1, magnetic susceptibility which is -1, and magnetic permeability, mu r is 0. So these materials used in to develop develop magnetic levitated trains, or you can say or bullet trains. These materials are used to develop magnetic levitated trains or bullet trains. So, this is the basic idea about your diamagnetic material. Now, come to the another material, that is called paramagnetic material. Now, second is paramagnetic materials. Or paramagnetic materials. These materials are made from atoms which are having permanent dipole moment. These materials are made from atoms which are having permanent dipole moment, which are having permanent magnetic dipole moment, which are having permanent magnetic dipole moment. So, in normal condition, in normal stage or in normal condition, due to thermal motion, their atoms are randomly oriented. So, their net magnetic dipole moment is 0. Net magnetic dipole moment is 0. Now, when these substances kept in external magnetic field, so atoms of these substances align their magnetic dipole moment in the direction of applied magnetic field, but due to thermal agitation or thermal motion, alignment is only partial. So, that increases the net magnetic field inside the matter, net magnetic field inside the matter. So, this is the main characteristic of paramagnetic materials. So, paramagnetic materials are made from atoms which are having permanent magnetic dipole moment. In normal condition, due to thermal motion, their atoms are randomly oriented, so their dipole moment is your 0. When these substances kept in external magnetic field, so atoms of these substances align their magnetic dipole moment in the direction of applied magnetic field. But due to thermal motion, alignment is only partial. That also increases the net magnetic field inside the matter. So, we can say these substances attract magnetic field lines. These substances attract magnetic field lines, as well as, or we can say these matters shift from lower magnetic field region to lower magnetic field region to higher magnetic field region, into higher magnetic field region. So, we can make lines of forces diagram like this. This is the magnetic field lines. Now, the field lines which are going like this, that can be attracted like this. Field lines can attracted by this matter. So, lines of forces can be like this. So, now dependency on increasing temperature, or you can say magnetization. Magnetization in the paramagnetic material, magnetization in paramagnetic material, depends on applied field, and inversely proportional to absolute temperature, and inversely proportional to absolute temperature, because on increasing temperature randomness increases, so alignment your decreases, because on increasing temperature randomness increases, so alignment decreases. So, we can write, so intensity of magnetization is proportional to B naught by T. and this we can write here I is equal to your C B naught by T, and C further written as mu into H, that we can write here I is equal to C mu naught into H by T, and as we know I is proportional to I is equal to susceptibility into H, and this is your susceptibility is equal to your mu naught by T, where C into mu naught by T, where C is Curie point, C is Curie constant. So from here we can get one relation. The psi is the susceptibility of paramagnetic material, which is equal to your C is the Curie constant, mu naught magnetic permeability, and T is your absolute temperature of the material. The susceptibility is your inversely proportional to temperature. As temperature increases, susceptibility decreases. Susceptibility decreases means magnetization in the material decreases. Now come to the next point. Now next point is the ferromagnetic material. Ferromagnetic material. So like paramagnetic materials, ferromagnetic material is also made from the atoms having permanent magnetic dipole moment, but a small difference is there. When we are looking at ferromagnetic material, so in a particular region of the material all atoms are aligned in a one direction. So that region for which all atoms are almost aligned in the same direction, those are called your domains. So we can write like paramagnetic materials, these materials also made are also made from atoms having permanent magnetic dipole moment. Permanent magnetic dipole moment. Permanent magnetic dipole moment. But one small difference we have found here in these materials. In these materials, the atom in a certain region of within a material, the atoms in a certain region of material in these materials, the atoms in a certain region of material spontaneously align in same direction. Spontaneously align in the same direction. So the region in which in which all atoms are aligned in same direction called domain, called domain. So, first see the meaning of domain. Domain meaning is that suppose this is your complete a ferromagnetic material. So, in this material atoms having dipole moment, but if we are considering let one of the small region of this in this region, let all atoms are in this direction when their dipole moment in one particular direction. Similarly, if we are having another such region, in this region also all atoms have dipole moment in one particular direction. Similarly, suppose third another region if we are considering, so here also all atoms having the dipole moment in one particular direction. So, these all are called as domains. But in the paramagnetic material, what we found, there was no such region in which dipole moment of all atom is almost in the same direction. But this is the characteristic we found in the ferromagnetic materials. Now, what will happen when these materials kept in an external magnetic field? Now, when these materials kept in external magnetic field, so see the effect of that field. So, due to that field, due to effect of external field, domain in that direction start growing. The domain in that direction start growing. Likewise, see the same, suppose here if we are applying external magnetic field in this direction, so due to the effect of this external field, so we will have domain which are bigger domain or a bigger number of atoms who are aligned in that direction. So, here it can have in that direction and here in the reverse direction. So, this is called your growing domain. Growing domain. The domain, as we are increasing the external magnetic field, the size of domain your increases. So, magnetism inside these material your very large. So, the domain in that direction start in growing, and if magnetic field increases, size of the domain continuously increases, size of domain continuously or constantly increases. So, even it has been found, if after removing the after removing the external magnetic field, then also domain will remain in the same direction. Domains remain in the same direction, or we can say magnetism in same direction will last, or magnetism in the direction of magnetizing field will last in the direction of magnetizing field will last even after removal of field, of external field. So this is the main characteristic of these type of materials. But these type of materials, their magnetism is very, very strong, and their magnetism properties also depends on temperature. So see here, magnetization of ferromagnetic material depends on absolute temperature. So it has been found on increasing temperature, magnetism of ferromagnetic material decreases. So on increasing temperature, magnetism of ferromagnetic material decreases. So the temperature at which ferromagnetic material become paramagnetic material is called Curie temperature. So for ferromagnetic material, magnetic material after Curie temperature, susceptibility is given as psi is your C dash by T minus T dash, where C dash is constant and T dash is Curie temperature. So for iron T dash is equal to 1043 Kelvin. It means iron after this temperature it become paramagnetic substance or paramagnetic material. So, this is the general idea about your ferromagnetic material.